Iago? Yeah. Iago are going to tell us more about this. Well, have a good talk.
So hi, my name is Chris, and it's my colleague, Iago. We're from a company based in Berlin called Indocode. We do open source consulting, and among other things, we are working right now with a client who has us basically running 3 Androids on one Galaxy S3 with 1 gig of RAM. I think there's been a couple talks at this Fosdem about running multiple Androids. That's mostly based on Zen. I think Samsung's doing work. I was watching one of the videos, not from this Fosdem, but from another event, and they were talking about how they were having memory constraints on the Nexus 10 that they're working on with 2 gigs of RAM. So, you know, that's always kind of amusing for us with the constraints that we have. So this talk is actually as much for us as it is for anybody else, because if you have ideas or anything, please stop us and give feedback, or the questions will be very much welcome, and hopefully after the talk we can talk to you also about some maybe improvements that you have, some ideas that you have for improvements. Okay, so the first question is, what exactly is low RAM? And Google defines this in the recent, I think since about ice cream sandwich, about 512 megs. If you're at this level or you're below this, then you're probably going to have to look at some of the things we're going to be showing to improve performance, or just to modify it to your system so that it runs, so you get good performance from your device. So when would you really find yourself in this situation? There are actually several reasons why, you have no choice. Maybe you have a client, this is similar to the situation we're in, and basically you have no control over the hardware you have, the memory or anything like that, and so you're just told to do it, and so you're kind of in a bind, and you see that you do what you can. You could be one of these people who runs devices that are more than about 2 years old, and then you could be one of these rare people who actually likes to put an updated Android on these devices. I don't really know any of these people, but they do seem to exist. And then I think some of the more interesting things, you have Android coming into the embedded space, where a typical or a traditional embedded Linux was found. And so I think we'll be seeing more and more of that, because there are some features there that are quite attractive and makes getting it up pretty quick. And then you have what I just talked about, the virtualized Android. Actually, I should mention a little bit. We work for a company called Trust Core, and they're working on this security, high security Android. And so we have basically 2 user-facing Androids, and then we have a third Android that's pretty much everything taken out of it, runs on very little resources. But it talks directly to the hardware. So we have basically a layer where the user-facing Androids, they have no direct contact to the hardware. And we run this on a microkernel hypervisor. It's not Zen. And actually, I think the main developer for that is actually, I think David talked on the microkernel track. Okay, so let's move on and actually look at the layers where we actually tune things. Now, the first layer is the one that's most it's the one that's most accessible to everybody. But we can't really ignore this, because even if you're creating the device, you have to make decisions on what apps. For a browser, for example, you have the unmaintained browser that's there now, or you could choose something like Firefox, another open source browser. And if you look at these, you will see that they do things, one does things better than the other as far as memory management, and we'll actually talk about why that is. Okay, the next one is the Dalvik VM. As everybody pretty much probably knows, Android uses their own VM called Dalvik, and this was for several reasons: licensing, performance, etc. And we should also point out that they have a new one called Art, and so this actually might eventually be deprecated and not used, but for now it's still the default. and Activity Manager. Now this is the integral part of Android, and it actually plays a major role in memory management, and we'll look at just the memory management portion of this a little bit. And then we have the Linux kernel. This is usually the bottom layer. If you're like us and you actually run a virtual machine, you actually have one underneath it to worry about. But yeah, we'll look at a couple ways that the Linux kernel, there's some additions from Android, but there's also some upstream. There's a lot of, Android benefits from what's in the Linux kernel as it is. Okay, I'm going to start with the apps, and then we'll go over to the Iago for the dollar. Okay, so the apps. It's important for everybody, actually, all the apps, to manage their memory properly. This doesn't happen all the time, or I should say this rarely happens. But if your app manages the memory well, then the whole system will potentially be more stable. And so it's a good idea to do that. And we're not going to look at all these ways apps can individually manage their memory, but we're going to look at how the system tells the app what kind of pressure the system is under so that it can respond to that. And we're just going to look at it very briefly. So yeah, Google says you should implement on-prem memory to incrementally release memory based on the current system constraints. Now, on-prem memory, it takes a parameter, integer, and this is actually a trim level. And this will tell you basically how much pressure the system is under. You have two basic categories. You have your running apps, and then you have your cached apps. The cached apps are basically the ones in the background, and they're lower down on the L or E list to be killed if need be. And so this is roughly, we have it, this is roughly, the rows are basically for the urgency, and so, the moderate and the background for the cache. You could probably start doing something here, and you probably should, but really, if you get down to critical and complete, then you really, really need to do something. But yeah, that basically, memory complete means you're in the background, and if you don't do something very quickly, you will be completely off the list. Oh yeah, there was that seventh one, and this is on a trim memory UI hidden, and this is basically when your app goes into the background and there's no visible UI. You can do things like freeing your views and freeing your bitmaps and things like that. Okay, so I'm going to hand over to Iago now for the dollar meeting. Oh yeah, I'm sorry, there was one more. And this is this trim on-trim memory is that started in Ice Cream Sandwich, and so you still need to implement the on-load memory for older devices, and that's basically equivalent to the trim memory complete. Okay, so I'm going to hand it over now.
Okay, so DalVPM, as Chris said before, is the Java virtual machine that Android uses. So we're going to first look a bit at how Android already does some things to keep the memory footprint down. First of all, DalVPM is a register-based virtual machine, whereas the regular Java machine is a stack-based. So each one has its fans. There's a bit of discussion, but in the register-based virtual machine, each instruction is more dense in the sense that you have to put two registers to work with, whereas in the stack you just push or pop one register. But it also makes the code a bit larger. But they say it's more performant, so that's what they use. And an important feature of this is that it doesn't use the Java class files and jars. It uses a format called dex, and this is a format made for, it's a very compact format. So the Java classes have a lot of duplication. For instance, if you have an interface, an implementator of the interface, and a user from the interface, it records the name 3 times in the Java class file. So Dex addresses that and makes some more optimizations about that. The gain of space is quite high. So a text file is roughly the same size as a jar file compressed, but the text is uncompressed. And that is important because text files can be mapped directly to the memory, so the kernel can keep the pages from the file if needs to be. Yeah. Also, you might have seen, well, when you're updating Android, you see this dialog optimizing apps. And this is TextOpt. This program converts text file to optimized text file or ODEX. And yeah, it verifies that the file doesn't do anything illegal. And it also does some optimizations like through empty methods and stuff like that, static linking. Another way that Android saves memory is with the cycle process, which handles the spawn of new processes. So at boot, Cygot loads the common libraries that most apps use, and then it forks the processes, so every process spawned by Cygot can share everything. And that's a big memory gain. And yeah, lastly, in Android 2.2, they introduced the just-in-time compiler. And yeah, they were saying that at first you can reach a twofold improvement, but in the new KitKat guidelines for low memory devices, they say that that for low memory devices we should disable it because it takes memory this JIT cache. Yeah, I think I skipped all the points, but you get the idea. So you're probably familiar with this output, and it's the Dalvik VM in the logcat, and it's telling us what is garbage collecting. So there's 4 kinds of garbage collections. Here you can only see 3, because the last one is called GC before OOM, and if you get to that point, it's that you are going to run out of memory, so you don't want that. So the rest are GC explicit. This is when you call explicitly the garbage collector. You can do that in your app, or the framework can do that. For example, when a binder connection gets dropped, it runs a garbage collection. Yeah. Then there's GC concurrent, which is the normal garbage collection. And this runs when the amount of free memory goes below a certain threshold. We'll see a bit more in the next slide about this. And then there's GC for alloc, which happens when you're trying to allocate an object and the heap doesn't have enough space. So it has to do a garbage collection and then grow the heap to make space for that object. And how can you tune the heap so that you can put it the right way for low memory devices? Well, there's 6 properties you can set in product property overrides at build time. These are heap start size. This is the size that heap has when the app is starting. And then there's these 2 that are, sometimes are a bit confusing. Heap growth limit is the limit that the heap has for regular apps, whereas heap size is the limit that the heap has when you declare a large heap property in your Android manifest in your app. And yeah, that's not very good, because if the heap is larger, your app's going to perform slower, but some apps might need this increased heap size. And the next one is heap target utilization, which is what the garbage collection routine uses for knowing when to do garbage collection. And yeah, it's clipped to 0.8, so if you put more, it will be 0.8 anyways. And the last 2 ones, heap min free and heap max free, is the minimum amount of memory that has to be free. So if you go below that, it will grow the heap automatically, and max free is the opposite. Now I'm going to talk about a bit JIT and why Google asked for disabling it. You can read there. For really low memory devices, we recommend JIT to be disabled entirely. Why is that? Because for when the JIT translates the bytecode to native code, it needs to store it somewhere. So Android has a cache for the native code in memory. And they say that if you disable JIT, you can save up 1.5 megabytes per process. Anyway, you need to test if it's really worth it, the performance, the loose performance for the memory. And it's funny because in our case, in our virtualized device, we found that we had increased memory, but also increased performance. But that might be explained because our system has a very slow I/O, and yeah, we need to investigate more of that. So yeah, I'm gonna hand over to Chris again, and he will talk about Tip Manager.
Okay, hello. Okay. So actually, I want to go back to the last point I was making about the trimming. We had found. And just to give you an example of apps that basically do it well and apps that don't maybe do it so well. So people probably know that there's a default browser in Android, and now I think it's unmaintained. Basically, Google's doing Chrome now for Android. But we found when we were looking we found that the browser was one of our biggest problems as far as memory users, and it wasn't really reacting to the memory pressure well. And we found that, for example, Firefox on Android was actually doing at least something, and it was basically it improved our stability quite a bit. So we're eventually going to be moving to that, which is quite nice. Okay, sorry, on the first slide, yeah. Okay, so Activity Manager is pretty much a central part of Android. It does a lot of things. We're going to basically be looking at very briefly at the way it orders your applications by priority, and then it uses this information that it's maintaining to basically tell the low memory killer, which apps have which priority, etc. Okay, so yeah, so Activity Manager, it's always maintaining a list of the applications and the importance to the user or to the system. There are the most important are the system apps, and then there are the foreground apps, which have, of course, high priority, and then you have things like what are called acceptable apps that are running, processes that are running. And these are things like if you have a music player, it might not be in the foreground, but it's important that it doesn't crash because a user probably doesn't want their listening enjoyment to be interrupted. And if you see here, I should have probably put it, but this is actually, all these declarations are in the process list.java in the Activity Manager code. And so what you see here, it's similar to nice values, where the largest number is the least important, and then the smallest number is the most important. Now these correspond to values that the Linux OOM takes for their OOM adjust value. And we can see here at the top, you see hidden, KitKat, that actually changes the cache. Because I guess it seems to describe it a little better. And you see at the bottom it goes down to -16. These are system or the system category. There is actually another value that's, if you use -17, that will basically say remove it from consideration of killing because and so it's taking it away from this management system basically. And you may need to do that for apps or processes that really need to stay alive. Okay, so it uses information, like I said, to pass it to the low memory killer. This is this is kind of a prelude to the kernel changes we're going to talk about a little bit. But it's important to talk about it now because this is the Activity Manager and the low memory killer kind of work together because the Activity Manager basically feeds the information to the low memory killer with its sysfs interface. And yeah, so it basically tries to preempt the OOM. Android never wants to get to the case where it's really out of memory. And so the low memory killer just, instead of out of memory, it's low memory so that you can avoid actually reaching the level where you actually have to kill the system apps and things. Okay, so this is actually the interface we have, and if you do cat on these files, you will see these values. Now these correspond directly with the values that we saw that were defined before, the first level layer. Although I think if you print this out on a KitKat device, you will actually see different values because KitKat is now trying to use the more modern, instead of OM adjust, which is in the OM, which is the OM used to use, it now uses OM score adjust, I believe, which is what is current. The OM adjust is deprecated. There's more granularity in the OM score adjust. You'll see, I think, a maximum of 1,000. So yeah, and actually the low memory killer has changes now that actually if you feed it numbers like this, it will actually look for those and then adjust it to the newer mechanism. Okay, and then you can see the min-free. Min-free values, these are basically, these are, I believe, in pages, and so if it gets down below 10,000 so pages, it'll start looking for the lowest priority apps to start getting rid of those that need to, and then so on and so on. So these correspond to category, and then at the point at which they will be considered to be killed. And this is also in the process list Java file, and you can see here you're basically defining which categories that these are for. So all this kind of works together. You can see this is exactly this top line is actually exactly what you feed into the adjust values. Now this last two, this min and free low and the free high. Now Android in this file you have an algorithm that basically tries to find a nice value for your device. Our device is special, of course, because we have a very high resolution device, and we have very low RAM. So we did make some modifications to this, and so that we had something that ran better for our device. And so you want to know how this works. You can basically look at the dumpsys output, dumpsys mim-info. It'll basically tell you how your apps are categorized at a certain time. And you can see it starts with the most important and goes down. And so that will tell you how much RAM it's using. And then you can also look at dumpsys activity OLM. I should actually point out that for dumpsys and mim-info, you can actually give the process name. It'll actually give you detailed information about the actual processes running. And on KitKat, they've added actually a couple more categories, which makes it a lot more informative. It'll actually tell you how much the graphics layer is using, how much native memory you're using, and things like that. And that gives you a lot more useful information. Dumpsys activity OM, basically has three sections of that output. You have the OM list. This is the current list that we saw that we set before. And then it will give you a bunch of information about the process's OM control. You can see the second line in the output, or the third line, I guess, OM max. That'll tell you like the maximum as it can be. But then you can look over here. You can see what the current is. It goes off the screen a little bit. And so you can get a lot of information using this. And I'm actually going to be writing a blog post about detailed what each of these actually parameters mean. So if you go to our blog in the next couple weeks, it'll be there. And then you can see basically the garbage collector. You can kind of see what's queued up for the garbage collector. And so it's interesting output to look at when you're trying to debug why your system is running unstably. Okay, so I'm going to hand it over to Iago now.
Okay, so lastly, we want to talk about the kernel. As we just said before, Android has some modifications to the upstream kernel, but it also benefits from the features that are there. Yeah, features that were added by Android. are like weight loss, Ashman, and yeah, things like that. So the first thing is KSM. It's kernel same page merging. So this was a feature, it was thought for virtualized environments in the sense that when you have several virtual machines in one machine, you're probably going to have a lot of pages in memory repeated. So what this does is merge the pages that are repeated, and yeah, you only have one page really in memory. And this page is going to be read-only, and it's going to follow a strategy of copy and write. So when you write onto this page, it will get copied. So yeah, you will lose this benefit. And yeah, before we talked about Zygote and how it allows to share pages to the spawn apps. So this is more like the same, but the processes don't have to be related in a parent-child relationship. So it does with unrelated processes. Yeah. So this was added in the official KitKat for the maintainers of the device use. And you have to be a bit careful with this because when comparing pages, it consumes CPU. So yeah, probably you need to find the right values for this before enabling it. So how do you enable KSM? It's very easy. Just go to your CSFS and yeah, put a 1 there in the run, and yeah, put some values in sleep milliseconds, which tells you, which tells the KSM how much time should you sleep between scans. And you can also define the pages to scan, and so in each scan, we'll scan 128, for example, here. And you have to find the right balance for this. You have to test how it affects your battery and how it improves your RAM usage. And you also have to mark the pages as mergeable. You do this with the madvice function and passing this madb mergeable. So ASP KitKat only does this in the mmap function, as you can see here, and only does it with private and anonymous pages. So that's interesting because in CyanogenMod they've been using this for a longer time, and they do it when the Zygote forks the processes, and they do it with the heap and stuff values. So that's interesting. And how you find if it's working? Well, just ask our friend Damsis as usual. So with Damsis info you can see the amount of memory saved and the amount of memory shared. And yeah, we reach values of like 20 megs, 25 megs in our device if it runs enough time. So the other feature, I should mention that the KSM, it's in the upstream kernel. And whereas this extra 3 kilobytes is not in the upstream kernel. So I'm going to try to explain this graph. This is how the system looks when you're running out of low memory. You have these watermarks, high pages, low pages, mid pages. So when the memory goes below the low pages, the kernel is going to try to free pages with the daemon called case.d. So you are getting in a dangerous zone because if you get below the mean pages, you cannot allocate more memory. Only the kernel can do this for its own purposes. So you have to stop the app, and that's requesting the free page, and then free a page wherever you want. Wherever you can. So this often causes I/O, so it's very slow. You want to avoid that. And they added this extra 3 kilobytes feature for exactly this purpose. And so this extra 3 kilobytes feature, you put there a value, and it makes the delta between mean pages and low pages bigger. So you can allocate memory without running into this I/O. Yeah, in case of the also has more time to free pages. So in KitKat it's set to 3 times a screen with full resolution and full color. So they do that in order to avoid entering this mode. It's called direct to frame. Well, I hope you understand that because I got a bit messed up, but if you have questions about it, just ask. And I'm already Chris to wrap up.
Yeah, sorry. Okay, I should point out that, so this is pretty much the end of our talk, but I should point out that we're actually not running on the FD, we're running on Signage Mod, and we're actually on 2.10.3? We're at 1.3, it's 10.1.3. And so we often find the stuff in KitKat is actually, the importance for us for KitKat is that Google did a lot of work to improve this. One of the most important things they did is actually added a bunch of documentation. I wish they had done that earlier, because most of this stuff we found out the hard way. But now actually it's pretty, it's well documented actually. There's a page on the AOSP page, site for a look around. There's some guidelines also on the Android site as well. So it's actually improved the situation a lot. So like I said before, we're interested if anybody has any other inputs, you can ask questions or make comments, or we can talk about it afterwards. So I think that was it though. All right, thanks. You're close enough. I'll give you this.
I think there is another option to optimize the memories that is Zebra, which can compress the...
Yeah, and that's actually in their guidelines. And that's actually, that's in their guidelines. We found for our system, didn't really, we have unique characteristics of our system, and that was not something that was for us useful. Yeah, so, but yes, the ZRAM that's documented by Google as being helpful. Any other questions? Comments? Yes.
That's for future thing. There's the hash in the kernel name.
So that's just for the future. So there's the hash in the kernel mailing list. It's about the volatile pages. And what it does, it allows you to mark the pages volatile or non-volatile. So when your operating system is on pressure or memory, it's allowed to actually dump the pages. So you can mark the pages in volatile. If it gets under pressure, it's about to swap something, you just can dump it.
Yeah, I know that
Sorry, if you try to access the page from your application, it's going to give you send a signal, so you get the address, and then you can reload it. So the idea was that for browsers, I can only keep a page with a single tab, and I can dump everything else. Yeah. So if you open the tab, you can recompute, redraw, render everything again. Okay. But that's not even main
Yeah, there's some other patches we've been looking at. There's one to, actually, no, there's actually, I should say it's not really a patch. It's already actually in the 3.2 kernel, but we have still a 3.0 kernel. But I just backported something in the 3.2 kernel, which is interesting for us. But Android, modern Android already has it. But that basically improves the, so that you don't basically need less direct replaying in the allocation path. But I don't think that's related to what you were saying. Yeah, I would like to look at that.
And there's a thing, a prototype implementation of JMalloc using the volatile pages.
Yeah, I'll have to look at that. Yeah, if you can point to it. Any other comments? Yeah.
So this was very interesting. We have actually tried to see how the new application goes and we can try to implement using native code. Because there are a number of tools out there that try to do I'm wondering if, okay, I have not reached this point like you so far, but I'm going to get there in school, so I'm interested to know if any hints or clues for us, because maybe using the binary application, it uses J9 to communicate with Java, with the activity managers, it uses more or less memory, I don't know.
Yeah, it's probably something we should probably talk about afterwards, because I understand it. But yeah, I know there's some, yeah, I don't know, Iago, do you have something?
I didn't actually hear. So you can make it like
Running native apps instead of the Java in memory.
yeah.
You can use Kühl to write an application on Android or Delphi, and the way they communicate with the entire Android runtime is using J9. I'm wondering if you have seen anything around this, because normally native code uses less memory than Java code.
Not really, because the bytecode is more compact. Actually, the native code it has to be expanded to use the registers and everything. So
Oh, yes.
Yeah, so the native code, it's bigger than the Java bytecode. Yeah, and I was just thinking the same as you, and I researched a bit online, and it turns out it is. So I think it's not going to help much in the memory. I mean, in performance, maybe, of course.
Theo. Thanks for that.
That would be a great idea. I didn't even get one We are running on full custom That's even worse.
Yeah, no, a bit of gaffer tape will always do.
Did you try to make as much lyrics out of an Android DSP? No, we don't just take the code from the vendor. We have this to that one of the Oh, all right. Well, we do usually with we try to, we just do people and that's the that was why we said
That's fine, yeah. Nothing.
Yes, we did some backporting of BTRFS because they said use BTRFS. We couldn't backport the last version. We did a bit of backporting. Also, crazy stuff. We want to be that's the undercatches. We don't really care because we can't get any application because we uploading. We actually restored a lot of the files. I just spent a few days rewriting the battery driver because the other stuff. Let's say they decided to invent an algorithm which works lots of magic values. It doesn't always work. It's mostly simple fixing. We record they change the magic value somewhere where they have more magic values. So we had to rewrite it. We have a problem that the platform is basically forced to deal with most of the games under DSPs, and it's kind of like buying it like a car online. It's like, we have to design possible different things. It's kind of like going online, buying a car, and then you pick it up. So doors on the other side. It's like in the yes, it's not mentioned that the pictures only show the other side. It's pretty bad. Yes, they're kind of different being a big number of things and like we remove the shit that has to be options instead of memory. So it's not video. Joysticks. PS2 mod. So what do we need? There's just this stuff. PS2 mods, it's like early 2000s. They go through that's really crazy. Then there are your expected ones that work something that use doing something like modem and doing that back home.
now look a bit more at routing. Routing hardware box. I don't know if it was last year also, or 2 years ago. Yeah, 2 years ago. 3 years ago. And now we're going to get an update about all the new features. And I'll let Robert explain all about that.
All right. Yeah, thanks for being here to my talk, which is about a short update about what we did in the DevOps project during last year. And well, in fact, you might wonder that in fact you want to put Linux on the bootloader, right? In the end, that's usually what people want to do, and if that's the case, we are finished here. You can just ask questions, and we end this talk here. But in reality, there are some other things you need to take care of, and some other constraints in usual embedded projects. I must say that we are more or less working on embedded industrial devices, products, not so much on phones and other things you might want to associate with embedded Linux. Our devices are most times things like machine controllers, even machine interface devices and things like that. And in that area, there are a lot of interesting use cases where the bootloader plays quite an important role. And I will talk about those use cases a little later. For those of you who haven't worked with DevOps before and don't know the bootloader yet, I have a short introduction about what we are doing there, how it feels like, what the basic look and feel of the command line is, and what's in there. One of the main things we added during the last year is the free desktop bootloader specification and support for bootloader device trees, and finally some nice features like multi-in support capabilities, and in the end some questions and answers. So I start with the use cases here. So what you basically do with the bootloader is that the first thing we're doing is you load out hardware initialization. The CPU comes out of the reset, and you need to initialize some things like the memory, the flash, the PLLs, the clocks, and all these things. And after doing that, the second thing is that you need to fetch the kernel from somewhere. And this is where you need to find out about boot medium, which can be any of these here, depending on your use case and on your actual hardware. And when you fetch the kernel from the boot medium, you just call it to the kernel and start it, and from there, an embedded Linux system is more or less like any other Linux system where the kernel starts and all the root file system and this kind of things. On an embedded device, you quite often have the use case that you need to present a nice flash screen, like here, somewhere in the hardware initialization when you're up and running and have the graphics running. Then you need to show a flash screen here, and when you fetch the kernel in the background, and you don't want to have it flickering or blinking or anything like that. And when everything is finished here, then you just call into the application, and the application starts and takes over. So that you just switch on, have the splash screen, and then it moves on to the application. I have a short demo here, short video here. I hope that works. And you can see when it's at 0, we switch on. On the left side, you see the serial console of the device, and here you see the splash screen, and then 5 seconds after power on, the main application, this Qt application, takes over. And you see that the login, I'll show it again, the login comes even some seconds after the application is already running. So at 0, it is starting, switching on, console, bootloader, splash screen, new starting, system D, application running, and then over there, you can see that some seconds the login comes, serial console. So this is basically how such a device works. What you're seeing here is a 500 megahertz ARM 11 MX35 from Freescale in a real customer device in that case here. And this is basically one of our scenarios we have here. Another use case we have is that when the hardware initialization is done here, we, in some cases, cases we have a decision point here in the bootloader where we need to decide if we boot one of two different firmware slots. Like for example, if you're normally running from here and you're doing a complete image update of your system in field, even without network connection or even without permanent network connection, you download an image or a data image, you put it into the second firmware slot, and then you just boot the other one, for example. Or another scenario, another use cases, that this might even be more than one firmware slot, firmware slot A, firmware slot B for updates. And if something fails, if something goes wrong with the main control application or something like that, then you might just decide to go into some factory default or into some emergency Linux which just shows a splash screen which says, well, contact the service technician or something like that. So deciding between different firmware slots is an important thing, and in most cases this really needs to be done with the bootloader, because all the rest of the system can be exchanged during the firmware update. So next thing is a short introduction to DevOps. When we bought DevOps from U-Boot in 2007, there have been a lot of things with U-Boot we have not been really happy with. And basically it was that U-Boot is very much written in a microcontroller-like fashion. You have a lot of configure, a lot of defines where you can do things on compile time, and you have a lot of things which are really different from what we have learned in the Linux kernel during the last 10 years or so. The Linux kernel brought up a lot of new good ideas about how to write C code, how to make it well tested, how to do things in a really good way. And we tried to adapt these good ideas and take them from Linux and bring them into the bootloader space. Another iteration was POSIX. When we first started with DevOps, we thought that there are a lot of things which could be more POSIX-like, like normal command line or all these things. And when we tried that, it really helped a lot, and we got rid of a lot of strange things in the U-Boot, which made a lot of problems mostly during hardware. Hardware bring up is something we do in our daytime job, so getting new hardware on our desk which never run Linux before, and then trying to make everything work when you don't know if the hardware works actually. This is something where the bootloader plays an important role. Frameworks is pretty important. If you remember the old Linux 2.4, there have been a lot of drivers who just implemented interfaces. And today in Linux we have frameworks and mid layers in there which implement the interface and have an internal API, and that's something we do in DevOps quite often. File systems is also something we have in DevOps these days. We just borrowed the Kconfig frameworks from Linux, which gave us parallel compilation quite easily and all these things. We have a standard shell, one of the busybox shells, where you can use commands like copy, rm, ls, and all these things. We have real scripting, and so basically the idea is to get best of U-Boot and Linux and mix that together and still do it bootloader way without interrupts, without having things in parallel and these things. So here is a typical startup from DevOps, how it looks like. You get a banner here and some messages about hardware stuff, and then this typical countdown here. Even that is scripted in DevOps. Can be thrown away, you can do it differently and all these things, and then we get a command line and can do things here. We have our file systems, basically the run file system which is mounted to slash with real mount points and things like that. We have a device file system mounted to dev, and the environment is copied to that path here. And then we have a standard command line that very much feels like Linux. So if you're doing Linux usually, and you're doing bootloader stuff, then this will feel really familiar. From time to time you do things like typing Vim or something like that. And sometimes one really forgets that this isn't the real Linux. And you can do things like that and see things here and If we have device nodes and that here, you can see this. And one really important thing if you bring up hardware is that you are able to access memory. Look around, look into registers, try to find out what's going on, things like this. And what we are doing here is that, for example, there's this MD memory dump command here, and that usually works on that MEM. You can just look into the ROM bootloader of that processor here, and if you don't want to access the normal physical memory, you can also use one of the other drivers available, like in this case here, one of the Ethernet PHYs, and if you add the word switch here for 16-bit access, you can see that you can just access the 16-bit word register this PHY. This is pretty much debugging stuff, just find out what's going on in the hardware and well, to bring up new electronics. One of the most interesting concepts is that if you have a file system, you can just start copying things around. You don't need any special commands for that anymore. Remember fetching the kernel from somewhere and putting it somewhere else in some other address. When I worked on U-boot, I just confused all these hex addresses, where you had to copy the kernel to and all these things. And all this becomes much easier, like if you look at, for example, this here, this is just copying from def-net 0 to, well, to somewhere in the file system, in the run file system, and you can just say, I want to use this device, and you don't have to remember where this device was and what the correct access was. It's quite comfortable. It's also possible to add partitions, like, well, when the kernel starts, it usually needs some idea about how your flash is partitioned, NOR flash, NAND flash, all these things. And we have an add part command in DevOps as well, and you can just give it a string here, which specifies layout of partitions, and DevOps is able to access that, and it's exactly the same syntax. Like what the kernel needs, you can just take that over to the kernel command line and continue there. Quite comfortable as well. Another interesting concept is device variables. For example, a device like the first Ethernet device here can just have parameters. If you use the definfo command here, you can call definfo ETH0, and then you see what the driver outputs for this device, and here you can see what kind of parameters it has, like the IP address and so on. And you can just set it like a variable, like this here. So setting variables for devices is quite easy. Also getting the kernel like TFTP, for example. Recently in DevOps we are more going towards having, well, things automatically mounted, so you can even copy things from the TFTP file system and things like that. So that's all quite easy and very abstract if you compare it to how it's done to do, for example. Okay, so this was basically a short introduction for those of you who are not familiar with DevOps yet and didn't work with the bootloader in the past, just to get a little bit of an impression how it looks like. And the next thing I want to talk about is the free desktop bootloader specification. And if we remember this image here, where we actually started the system here, came to the decision point, and then wanted to call into one of these, well, call it distributions or Linux systems, then we have, in fact, we have one problem. When you have actually started the kernel, then it's quite clear how the next steps look like. You can give the root file system variable to the Linux kernel command line and tell the kernel where it finds its root file system, and all these things are quite clear. But at this point here, where you need to do things, where you need to find out where your root file systems could be, there is something like a gap in the specifications, because when all these things came up, hardware was quite fixed. There was no big, well, hot plug buses like USB memory sticks or SD cards or anything like that. When U-boot was written, you basically knew that you had some NOR flash or NAND flash or something like that in your system, and there was nothing dynamic in that. Today, especially if you don't look at these deeply embedded devices, but at things like netbooks or more PC-like devices, then quite often you can just plug in an SD card and start from that, and you basically don't know anything about that. You want to look inside, you want to introspect that, and you want to find out what's in there. And this is basically something where we have a gap in the specifications. We looked around how the big distributions do that today, especially on different ARM targets. And for example, if you look at how Ubuntu works on, for example, the x53 Quickstart board or the Panda board, the Toshiba AC100 or OMAP3 Eagle board, then we find a lot of readmes or how-tos. Do this command, take this one, and then a lot of instructions you need to do in the right order, and in the end you get your system out of money. Basically the same if you look at Debian on different ARM systems. It's also more or less how-to-ware. You look into some wiki, you collect your commands to do the right things, and then in the end it starts up. And when the kernel is up and running, then all the systems feel almost the same. Fedora, the same thing here. It's for every distribution. If you look at on which ARM devices they are supported, you will find that it's a completely different set. One distribution has been tested by some people on that hardware, and then another distribution on that other hardware, and they have written a how-to, and then it is supported. But there's no generic way. Here is where we have this gap between the bootloader and the kernel. And there's nothing which is unified in that area so far. So it's basically a manual process. As I told you, with a lot of reading, and in the end, the distributions do not have general ARM support for any board, which is available, but just for selected ARM-based boards. So some years ago, there was this nice commercial here in German computer magazines. Some company, I can't read this here, where some company said the open operating system doesn't only have advantages, it's all different, it can take, strange paths here. So this is basically the situation we have today. We have a lot of interesting hardware here, we have a lot of distributions here, and for any of these, you need to define something special. This is where the free desktop bootloader specification comes in, and this tries to fill this gap and tries to invent something here which can be supported for all these devices and makes it possible to discover what's in here. I'll show you some examples in the later. This is where you can find the bootloader specification. It's coming from the server people. You know that Debian GNU systemd, or how is it called? I don't know. Okay, these people have invented that, and what it basically does is it offers a standard method how to find a partition to use as root, and it defines these bootloader entries, which contain a drop-in text file per entry, where you can just describe one of your operating system images you might have on your SD card. So let's, for example, just take a laptop with an SD card, something like that, with different operating systems on the card, and these entries define what's in there. And then you can have a directory here with a machine ID, and in there you have kernel and init.rd, device tree, and so if you look at different hardware, this is what we currently care about. One of these embedded boards from the history here, or another one, the socket here, FPGA or video board, something like that. And you see that there's a completely different set of media, eMMC here, NAND, SD card, SDI NOR, or something like that. And what the bootloader does want to do is it wants to look inside, wants to find out what's in there, and wants to, well, either select one of those or use any algorithm to choose between them. So how does it find the boot partition? On MBR, this looks for a special partition with type OXVA, and on GPT it looks like for this studio ID here, and if it finds that, it uses that as /boot and looks for these entries. And the entries look like this one here. You basically just had a text file with a title, a version, a machine ID, options, Linux, init.rb, and we added the device tree to the specification. When you first write that on an embedded ARM, this option wasn't available. We brought that into the spec recently. And this is basically everything the bootloader needs to know about that boot target. And if you have this information, then well, that's basically all you need for one of that firmware slots I showed you on my first image over there. Okay, so what can you do with a bootloader specification when you have the system up and running? This is an example here from the famous Kühl netbook, which was one of the first ARM-based netbooks within, I think, MX51 or something like that. Cortex A8 CPU in the 800 megahertz range, the smart book. And if you have that up and running, you can use that kernel install command here, which is coming from the systemd project. And you can, for example, just tell it that you want to install another kernel here. And if you just do that from your updater or whatever, or from the package manager, then it takes care of these bootloader entries, of these text files, and it provides everything the bootloader needs when you start it for the first time to have another entry with another kernel, for example. So this is also communication between Linux user space and the early stage where you where you will use that. I don't want to update. Alright, so basically we have a simple configuration file, like if you remember props menu.list in former times, and we have systemd support for bootloader spec with a prime install script, and so you can just install multiple distributions in parallel. You can have Fedora and Debian and Ubuntu and whatever on one medium. And you can even have multiple kernels, pair distributions, and all that is just described with a config file. Bootloader can then auto-discover that, and what we did with that was we had one SD card, and we plugged it into several, well, completely different ARM CPU-based embedded devices, and it can just boot. Now remember what the kernel community is doing right now. They are working on getting one unified kernel for ARM, where all the decisions, if you are on one model or on another one, is basically done on runtime and not on compile time anymore, like in former times. And the combination of these two things make it really possible that we can have one SD card and plug it into different devices and just boots just by auto-detecting everything. Alright. So we have a good understanding of these boot targets now. When we started with bootloader spec, it already worked on SD card types, which are running in the X4 file system, or in the embedded universe, we quite often have the eMMCs, which is basically an SD card in the VGA case, which you can directly solder into your device. That worked right out of the box, and what has been added was open firmware device tree support, that we can also describe our hardware within our F-tree, and support for flash-based devices, real flash-based devices, NOR flash, and flash-based devices, and UBIFS. That was also what you have seen in my first demo of a little device, which just has NAND flash and booted from an UBIFS partition. Alright. The second thing which came in last year, Kühl barebox is support for the open firmware device tree. The open firmware device tree is, at least in my opinion, thought differently if you had asked me some years ago, but in the meantime, I think it's a very nice tool or method to just describe hardware, to declare what you have in your embedded system, everything which is not auto-discoverable, like having certain chips on certain addresses on your address and data bus and these things. And all that is done quite nicely in a declarative way in the open firmware device tree. And the more this is used in the kernel, the more we thought about that we, really need the same information in the bootloader space as well. In the bootloader, there are a lot of points where you need to access some hardware, where you need to do some decisions based on where the different devices on your hardware are, and in order to initialize them. And what we did then basically was that we added firmware device tree support also to barebox. So you can in fact use the same device tree you use for your mainland kernel and put it in barebox, and then compile barebox with that, and then it does all the initial hardware bring up from the device tree. It looks where all the devices are, which I2C devices are on your bus and which address and all these things, and that's the initialization from there. So from our point of view, remember we are doing a lot of Linux kernel porting to new hardware. This made it a lot easier to bring up Linux on new boards. For example, we have a lot of hardware boards we are working on with the Freescale IOX family, for example. And if I remember how that worked, let's say 2 or 3 years ago, it was always a lot of low-level hacking, a lot of programming, writing board files and these things, pushing things through the compiler. And if you compare that to how that works these days, it's basically writing an OF tree. So if you have written an OF tree and have described your hardware, have specified where all the devices are, when you're basically done, you just feed that device tree to the bootloader, to barebox, and it moves. If you've done everything right, of course. Okay, the same device tree can be used to start the kernel, so you can just hand that over from the bootloader to the kernel. Works more or less automatically. There are other nice features in barebox, for example, that you can runtime patch the device tree. We sometimes have the case that there are variants on the board, let's say with 512 megabytes of RAM or with 1 gigabyte of RAM, and if you can't auto-detect that, you can just, if you know that, you can just write a little runtime patch for the device tree and put that into barebox. And so you can just put it there, and then it loads the device tree, changes that entry to what you already know, and then handle it off to the kernel and start. It works quite nicely. An interesting application for that is the declaration of displays. We have one embedded system which is often used for the displays for train stops and that kind of applications. And what happens there is that if the display breaks and needs to be exchanged, and the technician goes up there and mounts a new display, and he doesn't know much about software, right? He just knows how to screw the display into the case and all that. And what they are doing there is that they just put that device tree snippet with a new display description onto a USB stick. The technician just puts it in. barebox just reads that description from the USB sticks and runtime patches that into the OF tree and starts over. And so the technician doesn't need to know anything but how to plug in the USB stick and get that description. Very nice and makes it quite easy to describe hardware. There's a downside in that, and everybody who has known this device tree in the past probably knows that device tree very much depends on the stability of the bindings. So since we have device tree based kernels, one of the reasons, or the most prominent reason why the board refers to boot is that something changed in the device tree and some other component didn't take care of that. The awareness for that grow quite a lot in the kernel community recently. And the kernel developers are really taking care of not changing those device tree bindings. It doesn't work in any case, and still a reason for boards not booting these days, but it has become much, much better than if you look 5 years ago. All right, some other goodies. For example, we have multi-image support in DevOps here. With multi-image support, it's easily possible, difficult to read here, it's quite easy to build multiple images from the same config. With the case that we have one DevOps configuration, remember that's just kconfig, we type make menu config and then you can change things. And sometimes you have a whole family for different devices with different CPUs, single core, quad core, or dual core or something like that, on a MX6 for example, or boards which are just a little bit different. Then it's possible, like with the kernel, you can switch on all the different variants in kconfig. And the build system automatically builds a lot of images out of that in one. It makes it quite easier to have just one compiler and you can generate a lot of other things, like quite a lot more better compile coverage and that kind of things. Then for these auto-detectable devices, there's a nice detect command now, so that on introspectable buses like USB or SD, we don't know before what's in there. And usually you have the situation that if you look on any boot what's on that USB bus, for example, this needs quite a lot of time. If you want to achieve fast boot times, like in my video, with 5 seconds up to the point where the application is running, then you usually can't probe all the possible buses, SD cards, and USB until then. And for example, in that case, I told you with the train displays, what it does there is it looks if a USB stick is connected, and only if it is connected, it runs detect and looks what's in there and tries to do something, and all the protocol level initialization, these kind of things. So that's also quite nice. Then we can, for development quite nice, you can mount all the devices at once with Mount-A. And this is quite new. This is an excerpt from the Pengatronics internal IRC from Friday evening, Friday night, now Friday evening here, and where one of the colleagues here is working on this television DVB-T device with an MX27 CPU on it, which just has a television receiver on one side, a network on the other side, and you can stream television to the local network. And on this device, he's working on NFS version 3 support in DevOps. And as you can see here, he can have a look at the file system on the server here. NFS version 3 is pretty important for us, because if we have that, we can basically get rid of the requirement to have a TFTP server for development. I mean, if you're doing bootloader development, in most cases you will probably have a TFTP server running, right? Because you need to fetch your kernel from somewhere. And you can do the same thing with NFS. And the interesting thing there is that you can use user space NFS daemon, and you don't need to install anything on the development machine anymore. Installing things on the development machine is usually something where you need to do a lot of things correctly. Choose the right TFTP daemon, that's not an easy task sometimes. There are so many different ones with different bugs and different features, and we try to get rid of that. And well, we're also working with PDXs that cross-build system, and in PDXs we have a feature where we can just run a command and then expose our root file system via NFS root, and now we can also expose the kernel via NFS version 3, all from user space without needing root access, and then the board can boot up and do more things. So it's quite new to today's knowledge, not even in the repositories yet. And I think quite an interesting thing which makes development a lot easier. Alright, so if you want to try that, here's the most important communication channel. The website, www.devox.org. IRC channel and Freenode, and we have this mailing list here, which is the main communication channel, basically, where you can send your patches, we have the Git tree and all that. You can find that on the website. All right, that's my talk. Thanks for coming. Do you have questions?
Okay, I've seen.
I've seen that you have also firmware update support in Barebox. Could you elaborate on that?
Firmware update in which sense? I mean, writing a kernel to some...
I don't know, I've just seen a menu option in the configure menu of Barebox, I don't know.
I don't know exactly what you mean. Maybe it's just something we can look later on and have a look at the sources. Maybe for FPGA.
Any idea of your market share? I mean, your competition is essentially U-boot, and do you have any idea on how many of those boards are choosing one or the other project?
Well, basically the thing is that we don't really see that as competition. I mean, it's all open source software, and for us, one of the most important things behind doing this is getting our problems solved. So we usually look at what other projects are doing. We are looking at what U-boot is doing. We are looking at what the kernel is doing from time to time. I mean, that's a nice thing. It's open source. You can just look what other people are doing. Just take something from there, port it over to your environment, and the other way around. I don't see this as a concurrent situation or something like that. It's just all this vibrant open source community and where you can, well, not invent everything from scratch, but a lot of this wouldn't have been possible without you would be there.
A quick question, what about UEFI support? Any advanced status?
Yeah. I think that Sasha Hauer, who's the maintainer of Barebox, has already looked at what's possible there. And there are also ideas like, no, I don't say anything. There are also some ideas how to implement that in all the interfaces in Barebox, but it's not there already. But it should be possible in some or the other way. Well, we continuously look around what's going on there, and basically the idea behind all that is being able to boot Linux somehow. The Linux universe is changing over the time, and also the methods how the bootloader and the kernel interaction is changing, and we don't really know what will happen during the next years. You know, there's all these heated discussion about ACPI on one side and UEFI and doing Kühl embedded text on the other side and doing more F3 and this kind of things. I think it's quite interesting to observe all that, and in the end, what we need to do is to make Linux good on the hardware, and whatever is necessary needs to be done with the open source components involved there.
So you mentioned at the beginning of the talk that you introduced some modern programming ideas into the bootloader. More specifically, I don't know whether I remember it right, but you have some kind of driver model for Barebox.
Yeah.
So assuming there's this Linux kernel driver I would like to have in the bootloader for whatever reason, what's your belly feeling? How hard would it be to port the Linux kernel driver to the bootloader?
I didn't understand the last part.
How hard would it be to port a Linux kernel driver to the bootloader?
Yeah, in general, that's pretty easy. In fact, the driver model in Barebox looks quite similar to what the kernel has. I mean, it was inspired from there. And what you basically need to do is you need to get rid of all the parallel execution stuff. Now, we don't have interrupts in Barebox. I mean, it's still the bootloader, although we have all those nice fancy things. things. And it's in some way, it's like if you look at Linux looked, well, back in the 2.4 days or something like that, where you didn't have SMP and these kind of things. So that's basically taking a driver from the kernel if you really need to, well, making it easier, remove parallelism, and then put it there. So it works quite nicely. In fact, we don't really like this. Because it's code application in the end, and we don't like code application like anyone else is working with that. But if you look at my use cases with all these fallback images and things like that basically doesn't work without any instance which takes care about that decision point or the algorithms, how to choose which partition and how to choose which filters. So this is basically what still drives that we think you need a bootloader even today, and things like just starting the kernel is no real option for most cases. There are valid use cases where this is an option, but there are a lot of real world use cases out there with real devices where that really doesn't work.
Thanks.
Other questions? Okay, then thanks for being here, and if you have other questions, you might also come.